this lecture is about root and ratio tests for determining convergence and divergence of a series, and these are very, very powerful and very, very useful in many situations. Okay, so the root test is the most fundamental test, and let me define what that is. If you have a sequence an, and suppose this limit exists. What is this limit? This one crazy limit, right? Absolute value of an raised to the power 1 by n. It's like nth root of an, absolute value of an. If that limit exists, not just limit of an, okay, this is saying nth root of absolute value of an. If that limit exists, okay, that's L, then it turns out if this L guy is less than 1, the series an converges. Okay, so this is important. So, not just the convergence of an, but you want something stronger, right? The convergence of absolute value of an raised to the power 1 by n, okay, nth root, something smaller, something that can blow up, something larger, okay. So, the nth root of an has to converge, and if that converges to something lesser than 1, that limit is less than 1, then summation an converges, okay. If that limit were to be greater than 1, then summation an diverges. Okay, both of these are very powerful and clear statements about what happens to the series when the sequence has some sort of limit. Okay, not the sequence itself, the modified version of the sequence, right? This is why, that's why it's called the root test, right? 1 by n, you're taking nth root of absolute value of an. However, if L is 1, this may happen in many cases. If L is 1, you cannot say anything conclusive. Both can happen. It may diverge, it may converge. Okay. So, this is called the root test. Okay. So, root test is very nice. We are not going to prove this. It's a little bit technical. I am going to skip the proof. It needs some manipulation, etc. But it's a very, very powerful idea. But you can sort of see the motivation, right? The sequence tending to 0 alone is not enough for convergence divergence. However, if the sequence, absolute value of sequence, nth root of that, it tends to something, and that is less than 1, then you can conclude about convergence. If it's greater than 1, you can conclude about divergence. If it is equal to 1, there is no conclusive result. Okay, but sometimes this nth root and all may be complicated to evaluate. You may not want to evaluate that. So, in that case, you can use something called the ratio test, and this ratio test is slightly less powerful than the root test. However, it's very, very useful in practice. It's much easier to apply than the root test. Okay, so if you have a series an, if these two limits exist, what are these two limits? This is our old limit that we saw in the root test, nth root of absolute value of an. This is the ratio, absolute value, but an plus 1 divided by an. Okay, you see that this is just the ratio. Yes, ratios are much easier to handle in limits than powers, no? So that's why ratios are very easy. So this, if both these limits exist, guess what? They have to be the same. Okay, so you can basically apply the same test like the root test, except that this limiting value L you can compute as the ratio and not just the root, not the root. Okay, you don't need the root, just the ratio. Again, the same sort of things apply, right? If this limit is less than 1, then it converges. If limit is greater than 1, if it diverges, and if it is equal to 1, it's non-conclusive. Okay, so these limits may not exist, right? When these limits don't exist, you have to use some modified versions of the root test and ratio test using notions like limit supremum, limit infimum. In this course, we have not seen those concepts. So, we will not discuss the most general form of the root and ratio test. This more general things are true than this, but we are restricting to the case where mostly these limits exist. Maybe 1 or 2 examples I'll show where maybe this limit won't exist, but this limit will exist. Okay, it can happen, but the other way cannot happen. Okay, so the root test is the most powerful one. The ratio test is slightly simpler and it applies with a slightly lesser validity. Okay, anyway, so we are not seeing the proof of these results. We will just accept them as it is, but we'll apply them in examples. Okay, so let's see that next. Okay, so here is a recipe. So supposing somebody gives you a series and you have to find out whether it converges or diverges. What do you do? Okay, so here is a recipe I'm going to give. In most cases, this recipe should work. And if if it gets a little bit more complicated, maybe it won't work. But in most cases, it will work. At least most of the questions we give, it will work. I'll also show you one case where it may not work directly, and you'll have to do something more complicated. Okay. So the first thing to do is to see if the sequence tends to 0. Okay. It's a very easy test. Just look at the an and find its limit as n tends to infinity. You've done that so much. No, we've done limits earlier in this course, so you know how to do this. If the limit does not tend to 0, the conclusion is immediate. Okay, it diverges. Okay, so you can conclude your job is over. However, if it tends to 0, you can't say anything conclusive. You go to the next step. The next step I would suggest is to use the ratio test. Okay, because the ratio test in general is much simpler to apply, and if it works for you, great. You can decide convergence, divergence. What do I mean by working? You take the limit as n tends to infinity, absolute value of an plus 1 by an, and that limit is either greater than 1 or less than 1. Okay, in that case it works. Okay, so you've got converges or diverges. However, the ratio test may result in being equal to 1, or it may result in no limit. Okay, so in those kind of cases, particularly if there is no limit, if it is equal to 1, it's inconclusive. Of course, you can try the root test as well, and root test may be inconclusive as well. So no limit is also an interesting case that can happen in the ratio test. Where no limit or inconclusive, you try the root test. The root test may work. If it works, again, it's great. Now, what is root test? You're doing mod an power 1 by n, nth root of mod an. You're finding that if that has a limit and that limit is less than 1 or greater than 1, that's great. If that also is inconclusive, then you're in a bit of trouble. Okay, so that's where you need to invoke like comparison test and use some clever ideas and see if you can do something with that, and then see if anything will work. Okay, so it's a bit harder if you come to the comparison test, as you can imagine, but let's hope that these things work. Okay, so here are a few examples. Here's a sequence 1 by 2 plus 2 by 3 plus 3 by 4. So in these kind of sequences, the first job is to write an as a function of n. So let's write that down. It's 1 by 2 plus 2 by 3 plus 3 by 4 plus so on. And so you can write an as n by n plus 1. Okay, so this is n equals 1, this is n equals 2, n equals 3, so on, right? So you have to guess this. You can imagine that this is n by n plus 1. Okay. So what's my first step? My first step is to find limit as n tends to infinity of an, which is limit as n tends to infinity of n by n plus 1. Wow, we have done these limits before, right? N by n plus 1, this goes to 1, right? So you divide by n, you get 1 by 1 plus 1 by n as n tends to infinity, 1 by n tends to 0, you're done, right? 1. So this limit is 1, so this sequence diverges. Okay, so easy enough. First example I gave so that this will work. Okay, the next example is a very famous number. This power series. This series has a number as a notation. It's called E. It's Euler's constant. Some of you may see it. 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, so on. Okay, so how do we do this? Let's try that. This it's 1 plus 1 by 1 factorial by 1 by 2 factorial plus 1 by 3 factorial plus so on. So what's the nth term here? So it's better to start with 0. You can also do otherwise, but it's better to start with 0 here. And the nth term is 1 by n factorial. So there's always a convention here. 0 factorial will keep as 1. Okay, so it's a useful convention. So an is 1 by n factorial. What is n factorial? 1 by 1 into 2 into 3 into all the way up to n. Okay, so it goes all the way. Maybe you can include n minus 1 if you like. Okay, so it goes all the way here. So n factorial, we know how to calculate. N is 2 is just 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. It just blows up very quickly, right? Because we have so many powers of values of n, n minus 1 and all here, it blows up. Okay, so clearly an tends to 0. Okay, there's nothing much. This is 1 by n itself is there. So an will tend to 0 as n tends to infinity. So we can't do just the first test alone is not going to work. So we can try the ratio test. What is my L? Limit as n tends to infinity, absolute value of an plus 1 by an. So this will be limit as n tends to infinity, absolute value 1 by n plus 1 factorial divided by 1 plus 1 by n factorial. So this guy, let me simplify, will get the absolute value you can get rid of. Everything is positive, right? So no need to carry that over. 1 plus n factorial times n factorial by 1. Okay, so this is just n factorial by n plus 1 factorial. What is n factorial? 1 to 3. So let me just write that down. Limit as n tends to infinity. N factorial is 1 into 2 into 3 all the way till n minus 1 into n. What is n plus 1 factorial? 1 into 2 into 3, all these guys will come, n minus 1 will come, n will come, and then n plus 1 will also come. So, all these guys will cancel, okay, and you just get 1 by n plus 1. So, let me write it carefully. Limit as n tending to infinity 1 by n plus 1. What is this one? This is just 0, okay. Alright, so the ratio test ended up in limit being 0. 1 by n plus 1 as n tends to infinity is 0, right. So, you get 0. So, if the limit is 0, then my L is less than 1, which means this actually converges. The ratio test worked, isn't it? So, it's a wonderful little simple example. The ratio test worked very, very easily. In this case, we had to do a little bit of algebra to do the cancellation, but then the ratio test finally ended up being 0. Very, very nice to see. So, this number E, Euler constant, is actually some number. It will properly converge. There is no issue with that. Okay. I hope you see that. Okay. So, the next example is a slightly weird example. So, let us come back to this. Let us look at that, the third example. Okay. So, let me do that. The sequence is half plus 1 by 4 plus 1 by 4. It's sort of artificially constructed to make something happen. So, you can imagine what this thing is. Okay. So, you can start with n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, so on. Okay. So, how do you write this? A n. Okay. So, there are two cases, n is odd and n is even, right. If n is even, a n is 1 by 2 power n by 2. If n is odd, a n is 1 by 2 power n plus 1 by 2. Okay, that is the correct way to write it. So, this involves a little bit of trickery, I know, but you have to write it down very carefully, right. So, you see n even and then the term, right. So, what is in the denominator? If n is 2, the denominator is 2, then is 4, denominator is 4, which is 2 squared, and n is 6, denominator is 8, which is 2 power 3. Okay, 2 power 1, 2 power 2, 2 power 3, 2, 4, 6, 1, 2, 3. Okay, so that is n to n by 2. Okay, we are able to see that, the power there. Now, if n is odd, for 1 you got 2 power 1, for 3 you got 2 power 2, and for 5 you got 2 power 3. So, 1 to 1, 3 to 2, 5 to 3, it is actually n plus 1 by 2. Okay. So, this is something you have to figure out, you have to have some experience, but for n odd and n even, this varies. Okay. So, that is the main idea. If you want to write it down, that is how it looks. Okay. Now, if you do a n plus 1 by a n, you will get a very, very interesting and easy thing. For this, you do not need the general form. You can just look at this and tell me, if a n plus 1 is equal to a n, if n is odd, what will happen? You will always get 1. Do you agree? A n plus 1 by a n, if n is odd, the next value is equal to this value, right? If n is odd, a n plus 1 equals a n. So, the ratio will become 1. On the other hand, if n is even, a n plus 1 is a n by 2, isn't it? It is going one half below, right? If whenever n is even, if n is 2, then it became 1 by 4. If n is 4, it became 1 by 8. It gets multiplied by half. So, the ratio becomes 1 by 2. So, whenever n is odd, it is 1. Whenever n is even, it is 1 by 2. The limit does not exist, right? You will have 1, 1 by 2, 1, 1 by 2, 1, 1 by 2. It does not converge to any one value. You can look at that epsilon. So, this one diverges. Okay, so, it is one of those odd examples where this happens. I was telling you the ratio test is not as powerful as the root test. But then, if you look at a n power 1 by n, what happens here? Okay, so you get here 1 by 2 power 1 plus n plus 1 by 2n if n is odd, and 1 by n power n by 2n if n is even. Both of these guys tend to half, or this one is equal to half, very easy to see. This one is equal to half. This one tends to half, right? So, if you as n becomes larger, it tends to half. So, this just becomes the limit in the limit as n tends to infinity, absolute value of a n power 1 by n is 1 by square root of 2, right. So, you see here that a n power 1 by n, actually the limit exists, it is 1 by 2, it is less than 1. On the other hand, the ratio test did not have a limit. Okay, it is one of those examples constructed just to show you how the root test may work and the ratio test may fail. Okay, so it's okay if you didn't understand it, but main point is for this sequence, for this series, the ratio test will fail. It has no limit. However, root test works, and you can decide that it converges. Okay, you expect this to converge. No, that's okay. Okay, let's come to the next one. 1 plus 1 by root 2 plus 1 by root 3, etc. So let's look at that. 1 plus 1 by root 2 plus 1 by root 3 plus so on. You may be quickly able to identify this. For instance, you should be careful. Sometimes you should be very quick on identifying this. So, this is nothing but summation 1 by n power q, and q is half. Okay, so you can quickly identify the sequence. It looks a little different. Identify this. So, this will have to diverge, right? Because q is less than 1, and you know summation 1 by n power q for q less than 1 diverges. So, very easy way of identifying the sequence. You can try many of your other tests, all of them will end up giving you confusing answers. You may not get very precise answers, but this simple notion that you know summation 1 by n power q will help you. Okay. What about this guy? 1 by 1 2 plus 1 by 2 into 3 plus 1 by 3 into 4, etc. So, let us try that. This is also interesting. 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4. Okay. So, n is 1, n is 2, n is 3, so on. A n is 1 by n into n plus 1. Okay. So, a n tends to 0. Okay. So, my simple root is out. Let us try the ratio test. A n plus 1 by a n, which will be 1 by n plus 1 into n plus 2 times 1 by a n, right. So, n into n plus 1 by 1, n plus 1 may cancel, but you get n by n plus 2. So, limit, okay, you not write limit, this tends to 1 as n tends to infinity. So, this also does not work. Let us try the, I do not know if we know enough to try the root test. Mod n is okay, it is just a n power 1 by n. So, 1 by n into n plus 1 whole thing raised to the power 1 by n. We do not know how to take limits of these kind of things. Okay. So, you may argue that maybe you know some other tricks, etc. for this limit, but at least this looks complicated. Okay. We do not know what to do about this, right. We have not studied such limits. Maybe we will study such limits later on, but you are not able to quickly see what happens to this limit, right. At least I am not able to very immediately see, but maybe there are, at least using the methods we have seen so far, it is not very easy. So, it looks a little complicated, but you can do something simple here. Can you, right? Let us see. So, can we do some comparison test here? So, in case all these things are not working, is there a easy way to do comparison? Let us try that. We know so many more series that converge now, right? So, if I look at this series, 1 by 1 into 1 plus 1 by 2 into 2 plus 1 by 3 into 3 plus so on. So, if this is my a n and if this is my c n, you notice here a n is less than or equal to c n, right, every term. So, here it is half, I am replacing this 2 by 1, so this becomes larger, I am replacing this 3 by 2, so this also becomes larger, replacing the 4 by 3, this also becomes larger. So, a n is less than or equal to c n, and what is this guy? This guy is just 1 by 1 plus 2 squared plus 1 by 1 plus 3 squared, so on, and this I know converges. Since a n is less than or equal to c n, this implies by the comparison test, a n converges. Converges to what exactly? Maybe we do not know, but this converges. So, notice how when the ratio test fails and when the root test is little bit more convoluted, the comparison test wonderfully works. Okay, so you got this. But this one I will leave it as an exercise for you. It's a little bit more tricky. I mean, you may want to do a comparison, like for, once again comparison may work, no? So 1 is there, and then 1 by 3, and then you have 1 by 5. Can you replace this by 1 by 2? But then 1 by 2 is larger, and then you may not get anything here. So it looks a little complicated. This one actually diverges as well. But you need some more additional mechanisms to do it. So I'll leave this as an exercise. You can post solutions on the forum if you think you know how to solve. This is a little bit more complicated than using the techniques we've seen so far. Okay, so once again, this colorful picture here shows you the recipe you have to follow. Most of the examples we see in this course, the first two, the ratio test or the n tending to 0 will work, but that's not it, right? So there are root test and comparison test. These things will come and help us later on in some rare cases, and we won't focus too much on those kind of examples. For us, the ratio test itself should be good enough for most examples in this class. Okay, thank you very much.